You don't have a choice, sorry.
Check. All right, welcome everyone to UCUR 2022. We are excited you're here. You've made it through the most difficult part of this conference, which is that registration thing that happened. So thank you for going through that with us, because we went through the same process. So apparently you know to point your smartphone out there, but we put that in case you didn't know. But that is the program. We have those QR codes around campus, around the different buildings. So you can find that schedule. The search function is now working. On Wednesday it crashed, so nobody could find any of their talks, which was also a little bit of a challenge. But it should be working now. And then we have the free Wi-Fi DSU guest. You just have to accept the terms and conditions. And then I think that's good for 12 hours from there. If you're from the other UC institutions, we also have the EDU Roam network. And if you had that set up before from your university, that should be working here as well. So we have 9 of the 10 institutions here today, so welcome to all of you. I think BYU, do we get most of the BYU people? Yeah. So BYU is the largest fraction of attendees. I think there are about 220 total. They were also the first abstract submitted to the conference, so I will give them credit for that. Everything else. And then you can also find the full schedule on our website, ucur.dixie.edu. And the Zoom links for all the virtual sessions are on there as well. Can we go to the next slide? Oh, so what is research? And that differs based on different disciplines, so you can go to the next. And this is what a lot of people think research is. Turns out, after working in a national lab with a lot of physicists for a while, this is what it looks like at the national lab. And the stereotypes do fit in that case. Next slide. So the Council on Undergraduate Research has a definition for what research and creativity are. And it's basically something new that you're contributing to a discipline. So everything that you've done and that you're presenting today is adding to that growing discipline. And somebody in the future will be able to see that and look back at you and see the work that you've done and build upon that at some point. And so that's what we're celebrating today, is what your additions are, what your contributions are to those academic disciplines. Next slide. All right, so we have the full program on your, oh, by the way, my name is Rico Del Sesto, sorry. You probably have gotten emails from me. I just checked this morning, and we've sent out 14,000 emails over the last 3 months. So I apologize. My email is going on vacation starting at 4 o'clock. On the bottom of your name tag is a ticket number and an abstract number. So the ticket number is your registration number. That's going to be for lunch. And then your abstract number is your abstract number that's in the program. So we have a pretty full program. One note about lunch is open from 11:30 to 2. So any chance you have to go down to the Gardner Center, that's your chance for lunch. It's just grab and go. There are tables set up there, but there's no set time for lunch. And in the program, we do have some suggested times based on where the talks are and presentations are throughout the day. Next slide. So this is what the program looks like in Oxford abstracts. You can search for participants, including yourself. Information has all the Zoom links as well as a campus map. Poster gallery, so everyone doing a virtual poster, those are now open for commenting and viewing. So you can go and see all those virtual posters. I think we have close to 80 virtual posters up on our poster gallery right now. Exhibitors are the virtual graduate fairs of graduate programs that are there to let you see what their programs offer. We also have some booths next to the lunch area where we have some live graduate programs there as well. Next slide. So oral presentations, please be there at the start of your session. You should have your talk on a USB drive. Each presentation is only 15 minutes, so that includes questions and answers. So please, to keep everyone on time, please keep it to 15 minutes. We will have moderators in each of those rooms. For posters, you can set up 15 minutes prior to when your poster session starts. And the poster boards will have your abstract number on there, so you just put your poster on where the abstract number is. Next slide. So this is a campus map, and I teach chemistry, so I have to rotate molecules around. So we're going to do that in a second. But you're here in the Eccles, and the conference is in the Eccles, the SET, which is the next building over, and then the Snow building, which is the next one beyond that. And then the Gardner is where lunch and the graduate fair are. So we're going to take campus and flip it over 180 degrees. Next slide. So that made sense, right? So we're looking that way, and your carbon atoms are to the right. And so that is the direction you're looking, so everything is to your left from here. All right, next slide. And since we are talking about campus, I would like to acknowledge that DSU is built on the lands of indigenous people, and this is our DSU Indigenous Lands acknowledgement. Next slide. So I do want to thank our research office, especially Lillian White and Alejandra Enriquez Roncal. They're our interns, and they made this conference happen. Next slide. And then to pull off a conference this size, we have a lot of people involved. I think we have over 150 people on campus involved to make this happen, including moderators, volunteers. So thank you to those for helping us. Next slide. Oh. Yeah. They definitely deserve an applause. And then if you haven't communicated with your research offices on your campus, this group of people are also made this conference happen, and we've communicated with them a lot. They probably received more than the 14,000 emails. But if you don't know them, please reach out to them and thank them, because they are there to support you, and they have been there to support you throughout this process. I'd also like to recognize Julie Hartley with the Utah Board of Higher Education, who I believe is visiting us virtually right now. And then also Tanner Markham, Utah State student, who is the student representative for the Utah Board of Higher Education. So thank you, Tanner, for attending and representing students in research and creative activities. Next slide. Is that it? All right, perfect. So thank you again for being here. Please attend as many talks and presentations as you can. Collaboration and discussion are great for the research and creative process. I'd like to bring up Dr. Michael LaCourse, who is our Provost and Vice President of Academic Affairs, to make some comments.
Well, thank you, Rico, and on behalf of President Williams and the entire Dixie State community, we want to welcome all of our friends and colleagues from across the state. I wasn't going to say this, but the picture that Rico showed reminded me of a story So I'm going to tell this brief story. Early in my career, I had a colleague who was telling his own story about working in one of these national labs. And he was a young researcher, and he was in the lab, and he was told that a general was coming in. They were doing military-related research, and he was new. He wasn't really doing anything yet, but a general was coming in, and that he was told to be ready to do a demonstration or show the general what the work was he was doing, but he wasn't doing anything. So he pulled a hair out of his head, off his hair, put it under the microscope, and when the general came by, the general said, well, let me see what you're working on. So the general was looking at the hair under the microscope and congratulated him on his scientific progress. So anyway, I don't know why I thought of that story, but when I saw Rico's picture, it reminded me of that story. So anyway, it's really a privilege for us to be hosting this year's conference. It's particularly we're particularly grateful that you all could join us face-to-face in person. I just returned from a meeting the last few days in an academic meeting in Phoenix, and there were probably 100, 150 people there, and just about everybody commented it was the first time in 2 years they'd actually been with people in a conference like that, so it was really great, and I think we all have learned to live and tolerate the virtual world, but it's so much better to actually be in person. So thank you all for making the efforts to be here today, and hopefully next year that the entire meeting will be totally face-to-face. So I do, Rico was able to thank the members of the organizing committee and for their work in preparing, but I just wanted to take this opportunity to thank Rico as a leader of this year's conference and to recognize all of his hard work as well. So we can give a hand to Rico, I'd appreciate it. And of course, I want to congratulate all of our students who are here from across the state to present your work. I think Rico did a nice job in laying the groundwork for all of your accomplishments and hard work and the impact of all of that work, not only on your own personal careers, but also on the advancement of knowledge. And so you're all to be recognized and for that effort. I know it's hard work, time-consuming, and many of you are also balancing your classes at the same time, engaging deeply in an area of research that you have an interest in. So. I welcomed you to Dixie State University, but in about 4 months from now, of course, as probably all of you know, we'll be changing our name officially to Utah Tech University. And there we go. So the origin of that name and part of the rationale for that name is that about 6 years ago, we made the decision here at the university to move towards becoming a polytechnic university. And then a couple of years ago, we adopted a new mission statement that recognized us, at least internally, as being a polytechnic university. That would be our aspirational vision for the institution. And really, in the state of Utah, it seems as though many people are unaware of what a polytechnic university may be. Other states, they exist, and people know what they are, but less so here. And so we often get asked, well, what exactly does that mean? And we have adopted the basic, what we call tenets of being a polytechnic university, which means career readiness, applied learning, deep industry collaboration, and then strong foundation in liberal arts and sciences. But it's a lot of words, so you can kind of summarize it as all polytechnics do by saying that the type of learning that you have at a polytechnic university is that you learn by doing, that it's much more of a hands-on type of learning experience than perhaps you may get someplace else. So our long-term direction here is learn by doing, and there's probably no better example of learn by doing than engaging in the research process. And so it's especially, we have special opportunity here to celebrate learn by doing by hosting this year's conference. So we're really excited about that. We're really excited about hearing all of the great work that's been going on and really celebrating all of your work that you've been doing as you learn by doing. In higher education speak, we talk about certain kinds of activities that students are involved with that potentially have the potential to be transformational in your life. And we generally categorize those or call them high-impact practices. And so in Utah, actually, it's in a policy, state policy, that all students are to be engaged in at least 2 high-impact practices while you go to school. And so there's a whole list of what high-impact practices are, but I personally believe that the most impactful of the high-impact practices, the one that has the greatest opportunity for transforming one's life, is to engage in undergraduate research. So in my mind, this is sort of the epitome of the top of all the types of experiences. So the fact that you have identified a problem, that you have been persistent in pursuing a solution or an answer, or at least a tentative answer to a problem, means that you've had to engage in a way that is beyond what you may learn in a classroom. And I imagine that for many of you, this experience, if it hasn't been already, is likely to be transformational in some way in your life. And I want to give a short story. I like stories, so I'm going to give a short story about a person that I think exemplifies what a research experience can do in terms of transforming one's life. And this actually occurred at a previous university that I worked at. I was a dean of health sciences before, and this was a regional university, much like where we are right now here at DSU. But I was sitting in my office. I'm the dean of health sciences. A student who I never met before makes an appointment to come in to see me. She comes in and says, I'm applying for a PhD program at Johns Hopkins, and I want to study something related to the health sciences, so I would like for you to write me a letter of recommendation. I said, well, I don't know you. I'm happy to write a letter for you, but tell me something about you. What's your background? How did you get here? Why do you want to pursue your PhD studies? So she told me this story that she had come from a very small town in rural Texas. And of course, for those of you that know, there's a lot of small towns in rural Texas. And so she was one of these small towns and went to a very small high school, didn't really have much opportunity for learning at sort of an advanced level. Had come to the university, was kind of a shy, introverted person. But in her first semester, she was taking a chemistry class, and something happened. I don't know what it was. She didn't even know, but the professor must have seen something in her that sparked an interest and asked her if she would be interested in working in her lab and just to volunteer. So she just agreed to do that. I guess she's probably somewhat intimidated that she was even being asked to do this. So she starts working in the lab as a freshman and continues to work throughout all of her 4 years at the university, and sometimes as a volunteer, sometimes paid, sometimes for academic credit, but she kept on working and developed very advanced skills. She was working on a NIH-funded research program, and so by the time that she came to me asking for a letter of recommendation, she already had co-authored a publication, had a couple more that were in review, and had identified this career path. So I wrote her a letter of recommendation. She got accepted to Johns Hopkins to go work in a very large lab on her PhD. Following summer, she comes back to campus. So she comes in to see me. So I said, well, how's it going? She says, well, there was 4 PhD students that started with me. 3 of them had come from Ivy League schools, and then I had come from this public regional university. And then there was a whole bunch of other PhD students and a whole bunch of postdocs, all these people. I said, well, how are you managing it? She said, well, I'm the lab manager. I'm in charge of all of them. And I said, how did you do that? And she said, well, I just knew more than anybody else about how to manage a lab, how to run a lab. I knew how to operate all the instrumentation, the protocols, and so our mentor, or the lab director, just put me in charge. So I think there's a lot of takeaways from that story for me, and I've told that story a lot of times to a lot of people under different circumstances. But here you have a situation where a faculty member really initiated this by seeing something in a student. And I, having been a faculty member, and all the faculty members that are here can probably relate to those instances where you're in a class and you see something that, like, I think there's something there, and I'm gonna see where this goes. I'm gonna push the student. And so you do that, and you really don't know what the outcome of that is gonna be. But I think that was clearly a moment of transformation in that student's life, that somebody recognized that there was something there. And then, of course, the student, the persistence of okay, well, not a lot of confidence. I'm gonna go in, I'm gonna do the best I can, but I'm gonna keep going. And I'm gonna accumulate knowledge over time. And at the end of that, of course, the result is here she is running this, managing this lab at Johns Hopkins in her first year as a PhD student. So I think there's a story of persistence. There's a story of probably overcoming a lot of self-doubts. I mean, nobody gets into those situations without some level of self-doubt whether or not you can actually succeed. So you've got to push beyond that. I think even though that it's all new, it's challenging, it's going to push you in ways that you didn't think you could be pushed, or succeed in ways you didn't think you could succeed. So I congratulate all of you. I know that you, in different ways, you will be transformed through your experiences getting to today, and then certainly by the time you leave here today, the interactions you'll have with your fellow students and faculty that are here will impact your life. So anyway, congratulations again for all of your hard work. Congratulations for your commitment to advancing knowledge, and hopefully this is nowhere near the end of your journey. It's really just the beginning of where you'll go in your career. So with that, I'm gonna introduce the person who's going to do the introduction. So this is a two-step process. So anyway, I want to introduce Katie Sanders. Katie is actually, in addition to being introducing our guest speaker, is the Vice President for Academics for Student Government. And in that role, she and I interact on a very frequent basis. We meet all the time to talk about issues related to students on campus, and in particular academics. And so I will tell you the first time I met Katie a year ago when she became the Vice President. I said, well, what's your agenda? What's your priorities for this year? What do you hope to accomplish in your year as the Vice President? And she said, well, I really have one thing, and that is we want to get more students on campus involved with research. And so that's my objective, my goal for this year, and I'm pretty sure she's achieved that goal. So with that, I'm going to ask Katie to come on up and introduce our guest speaker. Thank you.
Good morning. Thank you all for being here. Provost forgot to mention that when I first met him, he said, so is this your office now, and I'm going to come meeting with you? And I said, yes, but not really, because that's very intimidating. Well, hello, everyone. Thank you for being here. My name is Katie Sanders. I'm a student here at Dixie State University. I'm studying biomedical science and chemistry. I'm currently the Vice President of Academics, as Provost said, and I've had many great opportunities and chances to do research and internships while I've been a student. So in fall of 2019, I was accepted and I participated in an internship at NASA Glenn Research Center in Ohio. And this experience really just changed my life and helped me find my passion in research. So because of that, I've had the chance to do much more research, and I have planned to go on to graduate school to study bioastronautics and biomedicine. And this leads me to our keynote speaker. And I'm so honored to be here to introduce her. Dr. Candice Hansen is a senior scientist at the Planetary Science Institute, and she works on NASA robotic spacecraft missions. After receiving her bachelor's degree in physics from California State University, she worked at JPL on the Voyager imaging team, and she received the NASA Individual Achievement Award for her Voyager imaging investigation contributions. While working at JPL, she continued her education and finished her master's in science in planetary physics and received a PhD in planetary science from UCLA. She was a co-investigator on the Cassini ultraviolet imaging spectrograph team. At this time, she received the NASA Exceptional Service Medal, Voyager at Neptune. Dr. Hansen is currently the Deputy Principal Investigator for the High Resolution Imaging Science Experiment on the Mars Reconnaissance Orbiter. She is also a member of the flight teams for the Mars Reconnaissance Orbiter and Mars Trace Gas Orbiter, the Juno mission in orbit around Jupiter, and the Europa Clipper in development. Dr. Hansen is awarded the NASA Exceptional Scientific Achievement Medal for her work studying You're going to have to repronounce this word because I am not going to pronounce it right. The Enceladus water vapor plume, and received the JPL Technical Excellence Award for her work with the Mars Volatiles and Climate Surveyor team. Most recently, she's responsible for the development and operation of the JunoCam, a camera and telescope on the Juno spacecraft orbiting Jupiter. For this, she received the NASA's Outstanding Public Leadership Medal in 2018. We're so lucky and honored to have Dr. Candice Hansen here to speak to us today. Thank you all for being here and being a part of the Utah Conference on Undergraduate Research. Sorry, you're gonna have to repronounce that.
Thank you, no worries, no worries. Thank you, and thank you so much for inviting me to come and join you today. I carried my phone up here just so that I don't get carried away and talk the morning away, because that could so easily happen. Okay, so what you're looking at, I'm sure you all recognize on the screen. Those are the 4 giant planets in our outer solar system. I'm sure you recognize Jupiter, Saturn with its beautiful rings, Uranus, and Neptune. Well, I'm not going to talk about them today. Each of these giant planets has a large number of moons. And I am going to talk about four different moons that we refer to as ocean worlds. So, of course, we all know our personal ocean world here, planet Earth. But you may not realize there are other oceans in the solar system. And so what I'm going to go through is I'll say what is an ocean world and talk about why they're interesting. I was going to do a little sidebar on my career path, but I don't think I need to do that now. And it's Enceladus is that moon, although some people among us will pronounce it more things like enchilada. But in any case, we'll talk about exploring those ocean worlds and what some of the future missions might look like that could be a part of anyone's career in this room. Okay, so starting with the definition of what is an ocean world. Basically, an ocean world has a rocky core, an icy outer crust, ice water, because it's so cold in the outer reaches of the solar system. But the key thing is that they have a liquid water mantle. So the rocky core might have ice separating it from the liquid, or it might be all rock and then a layer of water and then the ice. And how do we know there's that layer of liquid in there? When you send a spacecraft close to one of these moons, you can sense a difference in the gravity signature. The moment of inertia is a little bit different if there's a rocky core and an outer crust. But the main thing really is that the magnetic field of the parent planet is distorted. And so Jupiter, Saturn, Uranus, and Neptune all have magnetic fields. You plop an icy world with an ocean in one of those magnetic fields, and if the water's salty, it'll conduct currents and it'll distort the field around it. So those are the things that we look for. And so where have we found this signature? We have found it at Jupiter's moon, Europa. We found it at Saturn's moons, Triton and Enceladus. And also all the way out at Neptune's big moon, Triton. So these are the 4 moons I'm going to talk about this morning. So they have their liquid layers beneath an icy crust. What are the goals? And these are long-term goals. We want to explore these ocean worlds. We want to compare these internal oceans to our own oceans on Earth. We want to evaluate whether or not they could be habitable. And finally, are they inhabited? Are there whales, electric eels, weird grungy algae? What might be in their oceans? And so that's why, really, in the big picture of things, they're so interesting. It's that search for otherworldly life. So on Earth, life is found wherever you find liquid water. There's life of some sort. And I can tell you that I've met with Earth oceanographers, and they're like, liquid water? Oh yeah, you'll find life. So we'll see. But the biologists in the audience will recognize the tree of life over here. What would that look like if it wasn't on planet Earth? And so not only is there the search for life itself, but so we ask the questions, is there life somewhere? Is there life anywhere that, in the case of the Earth, you would fill in the blank liquid water? But on Titan, it might be methane. I'll tell you about that in a bit. Is there life everywhere? Is it just ubiquitous throughout our solar system? And under what conditions does life thrive? So those are the big questions. But that's the end goal. So let's back up and talk about where we are today. So where we are today is that a group of scientists got together and laid out a very systematic path of exploration, solar system scientists and astrobiologists. And so it's a step-by-step kind of a thing, because these are incredibly expensive missions, so you don't want to, mess up somehow. So the first step, of course, is to identify ocean worlds. Then once they've been identified, you want to characterize those oceans. You want to look at, what is a solvent? Is it water? Is it liquid methane? Is there an interface between the rocky core and the liquid water? And how do they interact? And is it habitable? Okay, what is the pH level in the water, for example? And then finally, after you've done all of that, then you send the spacecraft with the specialized payload to look for the biomarkers. So Enceladus is, if you think of this as a progress chart here, with Enceladus, we're all the way over here. And I will tell you a little bit more about how we got there. But we're ready, in terms of Enceladus, we're ready to go after the biomarkers. Europa needs a bit more reconnaissance. We need to really fill in the blanks over here. We need to access the ocean in some way or another in order to be able to know whether it's worth continuing on. Titan has a little bit more to be done, and Triton is still in the sort of circumstantial evidence, but not a solid foundation just yet. So in 1981, Voyager returned this particular picture of Enceladus. And we're very used to seeing moons in the outer solar system that are covered with craters. That tells you that the surface is very old, because most of the bombardment happened early in the history of the solar system. But we also saw this very puzzling, very geologically young terrain. And so it was like this huge mystery of how do you have this old terrain and this very young terrain, and what's the explanation for that? So as I said, I'm going to skip all of this because Katie did such a great job. And I'll just say I've been working in exploration of the outer solar system since my first job at JPL when I was 23. And I started just before the launch of the Voyager back in those days. I won't say what year. You'll be able to calculate my age. So anyway, we saw these puzzling terrains. So Enceladus was an important target for the Cassini mission. Cassini was a Saturn orbiter that was the follow-on to the Voyager discoveries, and we knew Enceladus was really interesting, and so it was an important target. So even though Cassini was in orbit around Saturn, we were always looking at when we could get close to Enceladus in that orbit. And so in February 2005 was our first close pass. And this is what I was talking about with magnetic fields being warped. So here's Saturn. This is obviously not to scale. Here is huge Saturn. It's got a big magnetosphere. I mean, the Earth, we're all familiar with our Earth's magnetosphere. Saturn has one giant size because it's a giant planet. But the field lines were, when the spacecraft flew by and we detected the field lines with the magnetometer, we could tell they were distorted. And so that was the real first big clue. And so then the magnetometer team asked the project if we could move closer. And so on our next close pass in July of 2005, we got within less than 200 kilometers of the surface of Enceladus, and we really hit the jackpot. So one of the things, in addition to being close, was that we flew by with a really good view of the south pole of Enceladus, and it's like right about here. And so all of a sudden, all this youthful geology made sense. We could see that there were fissures across the South Pole. And furthermore, there was a giant hotspot at the South Pole, which it shouldn't have been there. It should have been up where, you know, the sun was shining closer on the equator. With our dust detector on the spacecraft and the molecular detector, we could see water molecules that went up when we, and we didn't intend to do this, but the spacecraft passed through the plume because we didn't know it was there, so it seemed safe enough, but actually it was a little dicey. and then, you know, all these dust particles hit the spacecraft, so that was exciting, kind of. And so what we found is basically that Enceladus is spewing out its innards. There's water vapor and ice particles shooting out of these fissures that are across the South Pole. So how was I involved in this? And how was the instrument, my instrument in particular, playing a role in all of this? Well, scientific method, we started with a hypothesis. And our hypothesis was that current geologic activity was in some way responsible for that youthful geology. We were not the only people to say this. So we were not laughed out of town. But because of this hypothesis, we said, we think the way to look for gases from any kind of eruption there might be is to look at stellar occultations. And so a stellar occultation is what you call it when a star passes behind gas, or behind anything actually, and so you see the light being absorbed or scattered by the presence of that gas. And so in February, we had observed a stellar occultation that showed us absolutely nothing, just empty, completely empty space. The star went behind Enceladus, ignore those little footprints there, and came out the other side. We saw nothing. But then in July, with that south polar view, we watched a star go behind Enceladus, come out the other side, and on this leg, we saw that characteristic absorption that happens when a gas passes in front of your eyes. And so, your ultraviolet eyes. And so we knew immediately that this was localized, right? Because we only saw it here. We didn't see it here, here, or here. And so that was really the beginning of my research effort having to do with Enceladus. And that was really played kind of a major role in my career. So what's the nature of the research that you do with an ultraviolet instrument that has just observed a stellar occultation? So it's a little hard to see, but the blue line up here is the spectrum of a star when there's nothing between the instrument and the star. The red curve shows that when the star passed behind Enceladus's plume, some of that starlight was absorbed or scattered. And so we knew there was something there, right? What was that something? Well, what you do is you divide the occulted spectrum by the unocculted spectrum. Oh, and so let me just say, this is wavelength across the bottom here. So this is what a star that's bright at ultraviolet wavelengths looks like. That's what the spectrum looks like. And this is the count rate in 5 seconds of integration time. So when you divide the red curve by the blue curve, what you get is this crazy blue signal here. Very noisy data, but there were clear absorptions, and these absorptions right here are diagnostic of water. Only water looks like this in the ultraviolet. And so we knew the composition. You can calculate what the quantity needs to be in order to absorb this much starlight. And so by the end of Cassini's 13-year mission, we had observed 8 occultations of stars and one of the sun to probe the plume. And from that, we were able to write papers on the composition, the source rate, structure of the plume. There's supersonic jets embedded in this plume, and we were able to look at diurnal and long-term variability. So that was the nature of my research for all those years, was looking at these spectra and doing those calculations, and it was all really, really rewarding. There were other important findings from some of the other instruments on board. So I mentioned already the dust particle and the mass spectrometer. So this was the path of one of our flights with the spacecraft, and we went deliberately through the plume that time. And by then we had figured out it wasn't going to be dangerous to the spacecraft. And so we could analyze the actual particles coming out from the dust with the dust analyzer, and they were able to establish that there was silica in addition to the water crystals. The mass spectrometer found abundant methane in addition to the water, and simple organics and things like carbon monoxide and carbon dioxide. And so when you put all that together, you get a picture of Enceladus's ocean, with methane and silica coming from the rocky core and the interaction down here. And then it explodes somehow, and we really don't know how this part works, but it escapes into space, and that's where we were able to detect things in the plume and fly the spacecraft through the plume. So on my habitability checklist, liquid water, check. Organics, check. Are there hydrothermal vents? Why is that important? Those could supply minerals and other nutrients that life might need. What is the geochemistry of the water? Well, the jury's still a little bit out on the exact number, but it's somewhere between 8 and 12, so probably not too toxic. And, and then serpentinization is a chemical reaction that provides H2, which is something that life likes to eat, and that's still being studied. So there's enough yeses to ask the big question, is there life in Enceladus's ocean? And the wonderful thing about Enceladus is it makes it easy, right? All we have to do is get a spacecraft close, and it's got to have the right instruments. Of course, we didn't know any of this when we arrived with Cassini. So the Cassini payload was not really designed to look for life, right? But now that we know that there's an ocean and that it's being sprayed out to where it's accessible, we can go the next step. And pretty soon, and I don't know when exactly, but probably in the next decade, that mission will be underway. Okay, so now just to touch briefly, very briefly, on some of the other worlds. This is Europa. It's got an internal liquid layer, we know that, but we need to do reconnaissance. And one of the things we're trying to find on Europa is, where does the water from the ocean maybe reach the surface? Maybe along these grooved terrain, or and we could tell the surface is all broken up, so maybe there's a crack somewhere. So that's the point of the next mission, which is going to be launched in 2024. So the hardware is being built and tested as we speak. And so it will be a Jupiter orbiter, but it will go very close to Europa, and we'll be looking for things like plumes. That will be followed by a lander, probably in the 2030s, and that will actually take samples of the surface wherever the orbiter says, okay, here's a good place where the ocean might be making it to the surface. The next three are much more just sort of, hand-wavy concepts. But at some point, you'd like to send a penetrator down one of these cracks and openings. You'd like to study the bottom of the ice shelf, and you'd like to go all the way down and study the hydrothermal vents. So in the next 50 or 60 years, this is how things are likely to play out. As I said, plenty of time for you guys to get involved. This is the next mission to Saturn's moon Titan is a drone named Dragonfly. I love that. Anyway, Titan, as it turns out, has a very thick nitrogen atmosphere, thicker than our own. So it's a great place to fly things. And it's got 5% methane. Methane works like water works in our atmosphere. It turns to liquid, it rains, there's clouds, there's rainstorms, and there's river channels and lakes. But they're all made out of methane and ethane because it's so cold there that water itself is frozen. So that's what Dragonfly will be studying, is the organics in Titan's atmosphere and its sand dunes. And the launch date for that mission is 2027. So it's been through all of its preliminary design reviews, and they're starting to actually bend metal. And what about Triton, my favorite moon in the whole solar system? Only one mission has ever flown past, and that was Voyager. And so we discovered this very young surface. You can barely even find a crater on this surface. And it's got all kinds of weird terrain. We called this area up here the cantaloupe terrain because it looks just like the skin of a cantaloupe. And we get to name things. all kinds of fun. We also discovered little geysers erupting. And this moon is 38 degrees Kelvin. So it's like so cold. But in spite of that, there's geysers. Who knew? And so it's really time for a return mission to Triton. And that would be really exciting, because if we were to find, and this is really probably a century from now, maybe not quite that long, but if we were to find life in Triton's ocean, that would extend our habitable zone in our solar system all the way out to Neptune, which is really, really pretty amazing. So there's a convergence of science and engineering that happens in exploration, where scientists pose what are the questions are, what are the things we want to learn? You know, what are the hypotheses we want to test? And then we define the measurements. At that point, engineers and technologists take over, and they design the mission and the spacecraft and the instruments and the hardware and the software that we're going to need to achieve the science objectives. So I've worked very closely with these engineering design teams over the course of my career, and I'm happy to say in the last 2 years, I've participated in 2 different mission studies on how we could get back to Triton. So I'm going to wrap up here in about 1 more minute. So this is, again, what are the long-term goals? What are the long-term objectives? We want to identify ocean worlds. There's more than 4, but those are the 4 that we know for sure so far. We want to characterize their oceans. We want to see if those oceans could be habitable, and then we want to see if they are indeed inhabited. And so here's an artist's conception of what a mission might look like, studying. This is the ice shell above. It's in the ocean, and trying to understand what kind of, I don't know, crusty sea anemone might be growing there. It really takes a village. It really takes a whole entire set of skills and interests. You need your scientists to lay out the goals and objectives. You need your engineers, your technologists to design the hardware and the software to get you there. Technicians, these have to be built perfectly. You cannot go out and repair a bad solder joint. So we need world-class assemblers. Managers to keep everybody on budget and in schedule. Lawyers, why? Because typically we're launching nuclear material. You can't go to the outer solar system and depend on solar power for the most part. We need programmers. This is not the kind of stuff that exists in the cloud and you just purchase it on your Apple store. It's all really one-of-a-kind kind of code. It does no one any good if we up here are the only people that know about the results. You want the world to know what you're finding, what you're discovering. And so for that, you need reporters and educators. And inadvertently, I'm sorry, I left this off the list, we need artists. And artists are a big part of my JunoCam project right now. But it was an artist who made this beautiful graphic of what the future might look like. So I'll wrap up there, and now you can see the big four giants with their icy ocean worlds. And in the words of the Michelin Guide, it's worth the journey. Thank you. So we're going to have one more short presentation, but I wanted to tell you, I will stick around afterwards out in the lobby if anybody wants to come and ask me any questions.
Thank you. Thank you so much, Dr. Hansen. I'm just here to do a little segue. Thank you again for your fascinating research, your presentation, Dr. Hansen, and for warming all our brains up this morning. And thank you all for being here today. We're excited to learn about your research projects. My name is Brooke Hotez. I'm an English professor and assistant director of the research office here at DSU. We have a great day ahead with presentations, lunch, a graduate fair, and posters. Hopefully you found the UCUR program QR code by now. If not, you'll see it right outside. Find that, and that will list all the times, locations, everything you need to know for the day. We also have fabulous student volunteers around wearing red t-shirts, and so if you're confused on where you are and where you need to go, you can ask them and they'll help point you in the right direction. We also have signs all over the place. Great, and I just wanted to also mention that I am the editor-in-chief of our open access academic journal here at DSU called Curiosity. As Dr. LaCourse was mentioning earlier, you know, it's a great opportunity to transform your conference presentations into a paper and submit to our journal. We accept research from undergraduates, graduate students, and faculty alike. We really want to create a space where students and faculty could publish alongside one another and co-author their work as well. So please, there's some flyers and things out there about Curiosity. Consider submitting. You can submit a full-length manuscript. We have rolling submissions, or we are going to send out a CFP next week for a special issue on UCUR 2022 conference proceedings that we're planning. So please keep an eye out for that next week, and you can turn your presentation into a conference paper is like 2,000 words, where a full manuscript is like 5,000. So for the special issue, you could submit like a 2,000-word conference paper. We really hope you check that out and submit your work. All right, our first session starts at 10 a.m. It's almost 9:40, so you have a minute to wander outside and find your room. Thanks again, and enjoy the sunny day.